Hello there. So today I want to talk about Lie groups. And Lie groups are something that's basically graduate level mathematics. However, getting a basic intuition for what they're about is not going to be that hard. The reason that they're typically graduate level mathematics is that to define them formally and work with them rigorously is difficult, and I'll explain towards the end why, and if you want to get into more rigorously how to define them and work with them, what you should study. But here we're going to focus on basically a fundamental intuition for them and just talking about them a bit in general. And Lie groups are among my favorite mathematical objects. They're definitely a candidate for my number one favorite object, and they're extremely important to stuff I study because it turns out that they are extremely important in particle physics. So there are these things we call classical Lie groups, which are a bunch of different Lie groups that everyone kind of talks about very frequently. And so it turns out in particle physics, all of particle physics can roughly be explained by the product of three Lie groups. And so particle physics is extraordinarily complicated. Now, actually, I think you need 2 copies of all of this. But that's my opinion anyway. But so it turns out, of course, particle physics is very complicated, quantum field theory, all that. But you can kind of boil it down to this essence, more or less. But anyway, I haven't explained what any of that is. It's going to take some time to explain what a Lie group is. But I will first say, one, you already know some Lie groups. A circle is a Lie group. The rotation space in 2 dimensions is a Lie group. So you can kind of represent that as a circle. Because if you're going to rotate in 2 dimensions, you just need to choose one angle. So when I think of Lie groups, I kind of think of rotation spaces. So, for example, SO3 is... the reason it's called SO is it's the special orthogonal group in 3 dimensions. It can also be written SO3, comma R, meaning R is in the real numbers. But this is another Lie group, and it's referring to basically the space of rotations in 3 dimensions. Okay, so you might use a set of 3 by 3 matrices to represent that. So yeah, I'm often looking at these, thinking of them as rotation spaces. And this one, SU2, they're also, because they're groups, they're all about symmetry. And basically what's going on here is that normal, ordinary groups that you study in college, a college math course, those are not continuous groups normally. So, for example, the space of rotations in 2 dimensions, it's continuous, right? And yeah, so if you study group theory in college, you're probably never studying anything continuous. It's always typically finite. And so the Lie group, basically Lie groups are continuous groups. There's some technical distinction, I think, between the concept of continuous groups and Lie groups, but I'm not super clear on what it is. And if you're thinking that Lie groups are basically continuous groups, I think that you're not far off from the truth. I think it's almost true, but there's some kind of technicality there. Okay, and so this SU2 Lie group, basically this is kind of like the space of rotations on a 2 complex dimensional vector space. So SO2 would be this circle, the the space of rotations in a 2 real dimensional vector space. And SU2 I think of as the space of rotations on a 2 complex dimensional vector space. So we have a vector of 2 complex. Well, you often might see it represented something like this, beta b. So we have linear combinations in a 2 complex dimensional vector space. Okay, and the special here, if we're talking about a space of rotations, we want it to be sort of distance preserving, right? Like when you rotate something, you don't scale it. The fancy language that they use is they say it's norm preserving. But yeah, so these 2 complex dimensional vector spaces are what you see all the time in basic quantum mechanics. So when you're talking about the spin of an electron or the spin of any of the fermions, so the fermions are the matter particles in physics. So there's just, in terms of elementary particles, there's matter particles and there's sort of force carrying particles or energy carrying particles, which are they're called bosons. So the photon is a boson. There's the photon, the gluon. Gluon is for the strong force, which the strong force is SU3 here. And yeah, so there's 8 gluons for the strong force. There's the weak force has 2 bosons, which are the W and Z bosons, or it's like WZ plus or W plus or something like that. Anyway, there's 2 of them. And then you have the photon for the electromagnetic force, and then you have the Higgs boson, and that's all the bosons. But anyway, all of the fermions, the matter particles, so those are electrons, quarks, and neutrinos, those have what we call half spin. In physics, they call it half spin, but this is sort of very confusing language. But anyway, those fundamental matter particles, all their angular momentum, their spin, is represented by this SU2 Lie group. So it is showing up sort of all over the place. So, but I think of it as the sort of space of rotations on a 2 complex dimensional vector space. So yeah, anyway, so let's get into talking about how I'm going to explain Lie groups concretely, mathematically. And we're not going to have a rigorous definition because it's rather complicated, but I will point you in that direction at the end if you want to go there. But, and yeah, so prerequisites for this talk are going to be some familiarity with the exponential function e to the x. You will need, you want calculus, though you might be able to kind of skirt by. Is that the expression? You might be able to get by without it, but in particular, the derivative of e to the x is e to the x, which is a really nice property of the exponential function. And I'll also mention that a lot of times in math papers or math books, e to the x is written like this, just because if you're dealing with a lot of e to the x's, it's sometimes easier just to write or type out exp. So it's the same thing as exp. X is just e to the x. Okay. And we're going to use a lot of matrices, so familiarity with matrices is going to be good. In particular, if you're familiar with this rotation matrix in 2 dimensions, which looks like this. Some familiarity with this in particular is nice. So this matrix, if you multiply it times some vector, let's say x and y components, basically you end up rotating this vector by an angle theta, going in this counterclockwise direction by theta. And And I don't know, there's some interesting proofs of that, but or discussion of that. If this is completely new to you, I recommend first exploring, how do you rotate a vector in 2 dimensions? Just sort of search that online, and you'll find this matrix and find some explanations of where this matrix comes from and how it makes sense, so that it makes sense to you, because this is going to pop up. Okay. Oh, also, so getting back to the calculus prerequisite, we're going to use the Taylor series, and yeah, so that's from calculus. So that might come. If you're not familiar with calculus, that's going to seem a bit strange. But so the basic idea here for my approach in explaining this is we're going to use the exponential function, but we're going to do something interesting. And yeah, we're going to have x, but we're going to put a matrix up in the exponential. Now again, the exponential function is very interesting because of this property that it is equal to its own derivative. And that is right, there's this Euler's formula, e to the I pi equals -1. And we have, yeah. So there's a circle here. So I should say, but more generally, e to the I theta equals cosine theta plus I sine theta. So when we study rotations in depth, again in 2 dimensions, and we study complex numbers, this is quite valuable if you get to a high level. And this kind of construction is used all the time in physics and math. And basically, this is just the story of a circle and doing rotations using complex numbers. It's a neat package. And if you plug in pi into this equation, then you get e to the I pi, and so cosine of pi is -1 and sine of pi is 0. So you just get this. So it's just Euler's formula, or is it Euler's identity? Is that what it is? I forget. Is just plugging in pi into this equation. Okay. So vaguely that kind of makes sense to me. How should I put it? That as we move around a circle, there's something that is kind of unchanging. Like wherever I am on the circle, there's this tremendous symmetry. And if I'm moving around on the circle, there should be something that we can come up with. Well, there should be some connection between this, because as I move on the circle, in some sense, the picture is always the same. I can always define my position as angle theta equals 0, and in some sense, I can always look at the picture and say, nothing has changed. Even though I am moving around, I can always sort of move my coordinate axis. And somehow that should be related to this exponential function where no matter how many times I take the derivative, the story is unchanged. I don't know, that's sort of vague and hand-wavy, but I mean, it turns out to be true. Okay, so now here's the motivation for what we're going to do for going forward. We're plugging this matrix into the exponential. And in particular, I'm going to plug in, let's do -1, 1, 0, 0. So this may seem very strange, but we're just going to plod through it. We're just going to get through it. And in particular, we're going to use this definition of the exponential function, which comes from the Taylor series in calculus, where it is, let's see, well, it's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus x to the n over n factorial. So this is an infinite series which equals e to the x. And the way that where this comes from is that this is kind of Taylor series in general. If you have some function f to the x, you can approximate it. Let me see if I can get this right. We'll have the first derivative. I think I might make a mistake here, but valued at x to 0. It's something like this. You take the so this will be the function evaluated at 0. So actually, let's write it like that. F of 0 plus the first derivative of, I think, yeah, take that out. The first derivative evaluated at 0 plus the second derivative evaluated at 0 plus dot dot dot. And this is related to Newton. I think it's related to Newton's method of approximation, but this is a way of sort of calculating certain values of functions that you've come across in calculus. And so in the case where f of x, where our function is e to the x, we'll get e to the x evaluated at 0. We do e to the 0 is going to be 1 plus the first derivative is going to be e to the x. Here we plug in, I did something wrong. It should be, yeah. Anyway, it's the Taylor series, so I didn't prepare myself to talk about the Taylor series, but that's kind of a prerequisite. I'll have to prepare myself because I'm making some mistake in the explanation. But there's this formula, e to the x equals this stuff. And now what we're going to do is we're going to plug in the, instead of just having x, we're going to have x with this matrix. And you can kind of imagine that we're treating x like a scalar here, and we're just multiplying, so we get negative x, and we have x here in this case. Okay, so what we're going to do is we're going to take this matrix and we're going to plug it in to all of the x's, and x squared, x cubed, and so on. So what we'll get, I'll just write it like this, negative x, x, 0, 0. Now first, so actually here, I mean this also, by the way, you kind of, this is a e to the 0 here. We're kind of taking this, the 0th power of this matrix, which is just the identity. So this is sort of something that, if it looks super confusing, you just kind of have to take my word for it. But maybe I'll talk about this again later, this part, the identity matrix. Just take my word for it for now, that this is like the e to the 0 component. In matrices, so e to the 0 would be 1, right? And in the world of matrices, the identity is the identity matrix. So this is the thing that when you multiply it times something, you get back the something. When you multiply it times something, it doesn't change. And that's what we want. So that's what we're putting here. Okay. And the next thing that we're going to have is this x. By the way, do I have the cursor coming up? Yes, I do. Okay. We're going to have x times, and now it's, but our x here, you know, it's whatever was here. So it's not just x. It's this matrix, negative x, x, 0, 0. Does that make sense? Whatever was here, we're popping here, right? Okay, and then plus whatever this matrix is squared over 2 factorial. So the matrix squared over 2 factorial, and I'll just write 1/2 for now. And so we need to multiply this matrix times itself. So x, x, 0, 0, 0, negative x, x, 0, 0. What's that going to be? So we're going to have 0 minus x squared for this one. This will be 0, 0 for the next part. Bottom left element will be 0 plus 0. And the bottom right element will be negative x squared. So here, we'll just make this a minus x squared, 0, 0. Now, for the next step, we're going to have x cubed. So I'm going to need to multiply this times this same matrix again with zeros here. So let's just do that now. Let me do it. So it's here. So now for the first element in the top left, we'll have 0, 0. And this kind of pattern just keeps happening. Oh, sorry. Yeah, 0, 0. Then for the next element, we'll have x cubed. Then we'll have, for the bottom left element, 0 plus, sorry, we will have 0 plus negative x cubed. I might make a mistake at some point, but we'll get the mistakes fixed later. We have a way of checking. Okay, and for the last element in the bottom right, we'll have 0 plus 0. Okay. And then we're going to need to multiply this again for the x fourth term. Don't worry, it will a pattern will emerge, so we don't have to keep doing this. So I'm going to multiply it again times the matrix. And so here we get 0, we get x to the fourth. We get 0, 0. We get 0, 0. And for the last one, we get x to the fourth. Okay, so for the x cubed term, so we're going to have a plus 1 over 3 factorial times, it is going to be, what did we say it was? It was 0, x cubed, negative x to the third, 0. Okay. Now for the next term, 1 over 4 factorial. X to the fourth, which was just x to the fourth, 0, 0. And so this is just x to the fourth times the identity matrix. So actually, it's a little easier if I take the x's out, actually. Maybe I shouldn't have bothered putting the x in there. Doesn't really matter, though. So we have an identity matrix plus x times negative 1. Well, both of these pictures, both of these representations are useful, I think. Minus 1/2. Oh, sorry, I should put x squared. Right? Plus x cubed over 3 factorial times negative 1, 1. Plus x to the fourth over 4 factorial times, this is the identity again. So now when we multiply again times that matrix again, this is like the identity matrix. If you take the x to the x to the fourth to the outside, so we'll get an x to the fifth over 5 factorial time, or let's do it like this. We'll get this is x to the fourth over 4 factorial, and now we're multiplying. We're doing the next matrix in this whole pattern, this whole iteration. So it's x to the fourth times this identity matrix times this thing, which the identity matrix here doesn't matter, so but it'll be x to the fifth. This is where the pattern is going to emerge with a negative 1, 1, 0. So we get plus x to the fifth over 5 factorial, negative 1, 1, 0, 0, plus dot, dot, dot. Okay. All right, so how do we make sense of this? Now, we are going to make use of some other Taylor series, Taylor polynomials. So in particular, the Taylor series for cosine and sine. We're going to write this down because we're going to make use of it. So for cosine, it is going to be 1 plus, hopefully I don't make a mistake. There might be a mistake. I think it's going to be, it's going to be minus x squared for 2 factorial. You can look these up or just follow this. I kind of botched this explanation of the Taylor series, but look up the actual one. And it's very similar to what I was saying. And you can apply the same thing for cosine, where you do the evaluated at 0 plus the first derivative. I think these just need to be x's. That's all, not zeros. And then should be fine. Anyway. Okay, so the Taylor series is going to work out like this. You're going to have plus x to the fourth over 4 factorial. The next term would be minus x to the sixth over 6 factorial, but I'm just going to do plus dot, dot, dot. And for sine, we're going to get x minus, is it minus? Yeah, minus x to the third over 3 factorial plus x to the fifth over 5 factorial. The next term would be minus x to the seventh over 7 factorial, but I'm just going to do plus dot, dot, dot. Okay. Now, this stuff up here, which was this, we're going to write as one big matrix. Okay, we're going to add up all of the individual elements of the matrix. So e to the, can I zoom out here? I don't know if I can. Yeah, there's a zoom here. Okay. So e to the negative x, x 0, 0 equals, and I'm going to write it as one big matrix. So for the first element, we're going to have a 1, and then plus x times 0, which is 0, minus x squared. Now, matrices are, matrix algebra is linear. That means that we can just add and subtract these like you would normally. So x squared over 2, I'll write factorial, doesn't matter. Then for the next term, we'll have a 0, because x cubed times 0. Then we'll have x to the fourth, plus x to the fourth, over 4 factorial, dot, dot, dot. Now, let's do the bottom right term, because it's, spoiler, it's going to be the same. So for the first term, it's a 1. For the next term, there's a 0, then minus, yeah, it's just the same thing. X squared over 2 factorial plus x to the fourth over 4 factorial, dot, dot, dot. Okay. All right, now let's do the other ones. So for the top right term, we have a 0 to start with. Then we have minus x. Then we have a 0 for the next term. Then we have plus x cubed over 3 factorial. Then we're going to have 0 for the next term. Then minus x to the 5th over 5 factorial. Dot, dot, dot. Bottom left term. We have 0, then we have x. We have 0, and then minus x cubed over 3 factorial plus, bottom left term is plus x to the 5th over 5 factorial, dot, dot, dot. So comparing this story to the Taylor series polynomials for the cosine and sine, we then get that this is equal to cosine of x negative sine of x sine of x cosine of x. Okay. So this is very mysterious. E to the x times negative 1, 1, 0, 0 is equal to that. And so this is very interesting, very perhaps surprising. We can basically derive or create this rotation matrix. Remember, this is the same rotation matrix up here. We've just used x instead of theta. Right here like this. So in other words, so if I'm just going to replace by theta just for the looks of it. We have some theta times this matrix equals our rotation matrix. Cosine theta, sine theta. So by the way, you have the negative sign up here. If it's no big deal if you switch the negatives. So if you put a negative here and a plus here, you would just have a plus here and a negative here. It would just work out the other way. And this is just rotating in the opposite direction is all. So this is the way I'm writing this with the thetas is a counterclockwise rotation of theta, as we kind of normally do. And if you switch the signs on the sine x's or sine thetas, it will be a rotation in the clockwise direction. Okay. And wow, I'm running out of... okay, that's interesting. I'm running out of space on my canvas here. But so what this means is this whole business of e to the I theta, we can sort of replace it with the story with the exponentiated matrix. And what this means is that if you were ever extremely uncomfortable with imaginary numbers and how that relates to rotation, or just the whole idea of an I that equals the square root of -1, if this ever made you feel uncomfortable and you just are not a believer in it, you can switch the whole story to being about these exponentiated matrices, and you don't need I anymore at all. Now, for doing actual calculations, this whole I business is much more compact and just quicker. But now this is just the start of the story. So this represents a Lie algebra that we referred to as SO1. It's just the rotations of a circle. But there's much more. So if for your matrix you chose instead the matrix that you put in the exponent, if you chose this matrix, you end up with hyperbolic. After you do the exponential map, you end up with cosh x. and sinh. And these are basically the hyperbolic versions of trig. So these are sort of rotations on a hyperbola. So there's kind of the trigonometry we learned in high school, which is circular trig, trigonometry on a circle. And then there's hyperbolic trig is where at some point you learn about it, and it's like this whole shadow world. It's where instead of a unit circle, we have a unit hyperbola, and things are different. And that's the whole world where that sort of the stage on which special relativity happens. And so we have a bunch of fancy names for that. We call them Lorentz transformations. There's also Poincare transformations. And so these are isomorphic to a Lie group as well. But anyway, so the one that we looked at is SO1. So what you could do is you could, for example, sort of chain together different versions of this. So like if you have, first off, if you exponentiate the identity matrix, okay, you put this matrix in the exponent. After you do the exponential map, you end up with e to the x. You can do these out as an exercise. It'll be the same, but you need to know the Taylor polynomial, or the Taylor series for e to the x is here that I already talked about. But if you want to do it for this one, you need to know the Taylor series for cosh x and sinh x, which you can look up. But okay, so yeah, so if you do the identity matrix, you get this. So I could talk about complex numbers as some scalar multiple times this, which I could also represent as being some scalar, let's just call it alpha. You can map into this other version where you have some alpha or you know what, let's call it A and B. A and I, B, because of how multiplication of, the addition rule of exponents or whatever, this is an e to the a plus ib. So this is just the exponential map of complex numbers. So any complex number could be represented in this form, which is also this form, which is just some scalar multiplication, some scaling, and some rotation. So it's rather useful. Now, if we can also chain together, so some amount of the identity matrix. I just realized this is maybe very small for some people. So let's zoom in. Some amount of the identity matrix times, for example, some amount of rotation. This will work out to some so e to the alpha, which is some amount of scaling. So if you were looking at if you were looking on Google Maps and you're having an overall scale, you can represent it as with a matrix like this. Although you'll never, from this e to the alpha, you'll never get a negative number out. So that's fine. You don't really need to have a negative number for scaling. Times the stuff we just worked out, which is, it's going to be cosine beta. So some amount of rotation beta. So Lie groups are useful also for roboticists. So you kind of chain together certain things, certain it's like you have different linear transformations, right? We have a scaling and we have this rotation. And anyway, these Lie groups are really important again in physics, and it's a bit overwhelming at first, for sure. But I'm kind of exploring this all the time. I think it's very interesting if you add in, for example, let's say some gamma 1100, and you'll get the hyperbolic trig. So what this does is it creates a topological space where we have basically, again, it's like a rotation space. You have a set of possible transformations. Now, this example is not like a rotation. It's like a scaling. So it kind of depends on what you're talking about, I guess. And actually, including this, I think makes it no longer a Lie group technically. So watch out for that. The matrices that you use for Lie groups typically are traceless. So the trace of the matrices are 0 before the exponential map. But yeah, this is basically the continuous version of groups in mathematics. And I wish I could really explain the significance and importance of all of this, but it's hard to, other than just to sort of wave my hands and say, particle physics uses this all the time, and advanced mathematicians will very casually talk about different Lie groups, talk about SON, SON, SUN, and basically, again, I think of this as the rotation space of an n real dimensional vector space, and this is basically the rotation space of a n complex dimensional vector space. There's another one which is SP. This is called a symplectic group, but this is related to the position and momentum operators in quantum mechanics, if I remember correctly. So this is sort of the high-level, sort of expert way of tackling certain things in physics. And actually, Einstein was sort of not a fan of all this group theory stuff, but it turned out, especially when we looked at the strong force, it turned out that this stuff was pretty important, at least as a way of thinking. So if you can boil all of particle physics down to 3 Lie groups, that's extremely powerful. And you think about it in terms of that. And if you look at the standard model of particle physics, it has these exponential functions. Everything is like a e to the something, and there'll be what they call a Lagrangian. That's a whole other topic, but they'll have a bunch of Lagrangians represented in these e to the somethings, exponential functions. Yeah. And so you can look at special relativity and describe it in terms of a Lie group also. So if we're looking at unification physics, this is a really important prerequisite. If you're doing any study of unification physics, that means, unifying gravity, Einstein's gravity, with particle physics, or advanced mathematics. Lately, I've been studying something called algebraic geometry, which to me is the highest level of math that I've come across. There was this video on YouTube that was like a guide to self-study. They talk about abstract algebra and linear algebra and all of these sort of advanced college level math fields. They talked about algebraic, topology, algebraic topology, differential geometry, all this stuff. But they didn't even get to mentioning algebraic geometry, which it's pretty advanced because you need topology, you need algebraic topology, you need this Lie theory, we can call this in general, Lie theory, as prerequisites before you get into algebraic geometry. And also modern algebraic geometry also builds off of category theory, which I used to think category theory was like the most abstract math that there is, but then algebraic geometry comes along and builds on top of category theory. So that's what I've been studying lately, and the lecturers, the professors, and the textbooks will just casually talk about all these different Lie groups, the classical Lie groups. Okay, so in another video sometime I might list out all the classical Lie groups and sort of discuss them a bit. Also, I said that if you want sort of a more rigorous explanation, the thing is that you need topology as a big prerequisite. So, because these Lie groups, they form what are called manifolds. And manifolds are kind of like topological spaces, but slightly different. And I think they're topological spaces with some requirements on them. So you have to learn the fundamentals of topology, which is not an easy math course. Although it's sort of intuitive, but the fundamental definitions that you come across just at the beginning are hard to really to make them click in your head. So yeah, you're faced with these fundamental definitions that are hard to grasp, but the basic, overall it's intuitive topology because you're familiar with surfaces. A surface is a two-dimensional manifold, so the concept of a manifold is really just this n-dimensional surface, like a hypersurface. And manifolds are very important in general relativity also, because it's kind of, general relativity is all about manifolds. Okay, so topology is a strong prerequisite for this discussion of Lie groups. Lie groups, you make use of, they're sort of at the crossroads of topology, calculus, and abstract algebra. And the prerequisites are kind of tough. And when you get into rigorous definitions and rigorously proving things, it's heavy duty stuff. But the basic intuition you can sort of grab a hold of actually without necessarily understanding things with rigor. Okay. Anyway, so if you want to learn it more formally, you need to study topology first, then you can tackle it. And Lie groups are sort of they're just part of the basic language of advanced mathematics and physics, I would say. So I kind of had to get it out of the way because in future videos I will be casually talking about certain Lie groups. That's about all I wanted to say. So I know this was long, but thank you. Take care. Bye.